All right, everyone. Going on to the next part of what you'll need for the first assignment, line integrals. So up until now, you've learned how to integrate over different types of things. For example, in Cal 1, Cal 2, you learned how to do something like this. All right, this is where you're integrating over the interval from A to B. Right. Here you've learned how to integrate over a couple of other things, right? So you learned how to do double integrals as well. And that one we were integrating over, so we learned how to integrate over a plane region R. And then you've also learned how to do triple integrals, right? And this you are integrating over a three-dimensional space, cube. So today we're going to actually learn how to integrate over a curve or a line or a path. All right, so there are a couple of names for this. What your homework assignments in your textbook are going to call this are line integrals. So line integral, you integrate over some curve or some path C. Sometimes these are also referred to as path integrals because you're integrating over a path. All right, so you can integrate, it can be something in as many dimensions as we need, right? So you might see something like f of xy, f of xyz, right? You can do this in 2 or 3 variables. The thing is, our differential, what we integrate with respect to is something that we've seen before, ds. So remember when we talked about the surface area of a three-dimensional space or the arc length of a two-dimensional curve, right? This is the same ds. So the way that we've learned it before, specifically if we write a set of parametric equations, is that ds is equal to the magnitude of r prime of t dt. All right, and if you remember, that was just the square root of x prime squared plus y prime squared. There could also be a plus z prime squared. All right, so dt. So these derivatives would all be in terms of the parameter t. And that's still a thing that we're going to use in line integrals or path integrals. So let's just jump into an example. So for the first example, let's say that we want to evaluate the following line integral. So integrate over the path c, x squared minus y plus 3z ds. All right, and every time we do a line integral, we do need some kind of a description of the path c or the line c. And in this example, we're going to let c be a line segment from the origin to the coordinate 1, 2, 1. All right, so this is our given information. We want to evaluate the integral of this three-variable function over this pathway. And here's the thing, the three-dimensional function could represent all sorts of things. Like when we look at some application problems, this could be the density, so you could be integrating over a path to find the mass of something. This could be a force, so you could be integrating over a path to get the amount of work done on the object. Anything that this function could represent, you're now able to integrate over something that is not just a two-dimensional region, a three-dimensional space, or just an interval, right? You can make this any kind of path you want, which is actually a very powerful thing to have in our arsenal. So anyway, now that I've talked a lot about this example, let's do it. So key thing for this is being able to transform what you see in front of you right here into definite integrals that you know how to evaluate. The first step for that is going to be writing out parametric equations because we know how to write ds in terms of this guy, right? But we have to have parametric equations for x, y, and z. Since we're doing a line segment from the origin to each of these points, we can write using our starting value plus change t. So for x, the x coordinate starts at 0 because the origin, and ends at 1, so that's a change of 1. So 0 plus 1t, we get x is equal to t. Then for y starts at 0, y ends at 2. That's a change of 2. So 0 plus 2t. So y is equal to 2t. And then z starts at 0 from the origin, changes by 1. So 0 plus 1t, z is also equal to t. It's also important for us to note what the values of t are because that's going to serve as the bounds on our integral. So if I start at 0, all right, if I start at the origin and each of these coordinates is 0, I would obtain that by setting t equal to 0. So I know that the lower bound is going to be 0. To get to the final point, I would have to plug 1 in for t. So I know that t is going to be from 0 to 1. Now that I know my parametric equations, the next thing is to figure out how to write ds. So I know my bounds, I know what I can replace x, y, and z with. I just need to figure out the differential, right? So we know that we're going to need the magnitude of r prime. We know that that's going to be a square root of something, right? So the square root of derivative of x with respect to t will be 1, so 1 squared. Derivative of y with respect to t would be 2, so plus 2 squared. And then the derivative with respect to z would be 1. If I add these together, I get the square root of 6, which kind of serves as our Jacobian throwback. All right. So if I wanted to write this line integral as a definite integral, I would start with my bounds 0 to 1. I could also replace the x with t, the y with 2t, and the z with t. Then I replace my ds with magnitude of r prime, so square root of 6 dt. So if I simplify, combine like terms, and move my constant factor out, this is what we get. Okay, so we went from that to that. Pretty cool. Now I have to take my antiderivative. I'll get t cubed over 3 plus t squared over 2. And we're going to evaluate this from t is equal to 0 to t is equal to 1. I know if I plug 1 in, I'm going to get 1/3 plus 1/2. I know if I plug 0 in, I'm going to get 0. No need to write minus 0. Then adding these together, this would be 2 over 6 plus 3 over 6. So I get 5 square root 6 over 6. And that is the value of my line integral. So to summarize that process, we have to write our parametric equations and figure out the range of t if that's not already given to us, because a lot of times it is. From there, we have to figure out the magnitude of r prime because we're going to need it for the differential. After we get all of our information up front, we can rewrite the line integral by replacing x, y, and z using the parametric equations. And we can replace the differential using the magnitude of r prime that we got. Then from there, it's just integration. Okay, moving on to another example. So in the next example, we'll actually look at a path. So let's say that we have, so let's say that we want to evaluate the line integral of x ds over the path c. So the c that we're going to be given, the c that we're going to be given follows a path that looks like this. We start off at the origin. We're going to go out to the coordinate 1, 1. Then we're going to have a line segment that goes directly from the origin to 1, 1. And the arrow, remember, indicates the direction that we're moving along the path. Because whenever we parameterize or write parametric equations, that introduces a direction, right? Because increasing t, you're moving along that direction. The second part is, so we'll label this as the line y equals x. The second part, we're going to follow a parabolic arc back to the origin. And this parabola can be described by y equals x squared. So this is our c, right, the pathway. Now we have to write our parametric equations. We have to come up with ds. Here's the thing, though. We have two very different pathways that we need to integrate over. And as long as these pathways are smooth, meaning that meaning that both curves are differentiable, which they are, that's a line, that's a parabola, derivatives exist. Yeah. Derivatives are continuous, more importantly. Yeah, because both of these curves are smooth, there's absolutely nothing wrong with me dividing this integral or splitting this integral into two sections. We can have the path integral that goes over that straight line, y equals x. And then we can add to that the path integral that goes over the parabolic arc. All right, so same integrand doesn't change. We're just changing the paths that I wonder if I can stop lighting up the camera. Nope, too close to an open window. Anyway, natural light for the win. Anyway, whenever we have this case where we can divide our path into several pieces, that's fine. Another thing that I want to point out is that this is an example of a path that ends where it began, right? This is an example of what we call a closed path, right? And because this is a closed path, there's also a special notation that we could use to note this. You might see this when you take more advanced classes in your major. So the little circle indicates that this is a closed path. I could also draw an arrow. If you notice, this is along this pathway, we are moving clockwise. So I could also draw an arrow that indicates that we're going in the clockwise direction. Right, this is a fairly common notation in fields of study where there are a lot of closed paths. Right, but we're going to talk a lot more in depth about closed paths, what it means for them to be simple and yada yada in the next section. Okay, so anyway, I can split this into two different paths. All right, so when I do that, I would need to parameterize each one separately. So for C1, I could write parametric equations like I'm doing so for a line, right? So my x and y are, so my x and y are going from 0, 0 to 1, 1. So I'd get x is equal to 0 plus 1t, so x is equal to t, and y is equal to 0 plus 1t, so y equals t. The restriction on t for this one is going to be that t is between, 0 and 1. Yep, so t is between 0 and 1. Right, because I start at 0, 0. In both cases, t would have to equal 0. I end at 1, 1. In both cases, t would have to equal 1. Now for C2, the path that goes along my parabolic arc, think about it with x. I'm starting off at 1. I'm ending at 0. So if I wanted to keep the same restrictions on t, right, then I could start at 1. Wait, why am I writing parentheses? Blah, blah, blah. Rules. 1, and I could subtract the change times t. For y, remember that for the parabolic arc, y is equal to x squared, right? So whatever I wrote for x, y is going to be that, but squared. And you see the bounds for t still work on that one. When t is 0, x is 1. When t is 0, y is 1. When t is 1, x is 0. And when t is 1, y is 0. So we have our parameterizations for each path. Now we can now we can go and figure out what the magnitude is for, oh, yeah. Yeah, the magnitude of R for each individual path. So I have one for C1, right? And in that case, we have the square root of derivative of x with respect to t. That's going to be 1 squared plus the derivative of y with respect to t. That's also going to be 1 squared. So the magnitude of r prime is the square root of 2. Now, if I go to the second one, the second path, we want to look at the magnitude of r2 prime. So derivative of x with respect to t would be -1. Parentheses are important here. All right, then if I take the derivative of y with respect to t, I have to use my chain rule. I bring my 2 down, then I keep the base the same, take 1 away from the power, now that's to the 1, and multiply by the derivative, so we would multiply by -1. So -2 times 1 minus t, and then we're going to square that. So for the sake of simplicity, I'm going to keep this written as 1 plus 4 times 1 minus t, that quantity squared. Okay. So anyway, all right. So anyway, now I have enough information to go through and write the path integrals as just regular definite integrals. So over C1, that's going to be pretty straightforward because we already, like, everything's linear. The Jacobian that we found is square root of 2, right? So we know that t is going to go from 0 to 1. Those are the bounds. Then we replace the x with what we got in our parametric equation. So that's going to be t. And then we replace ds with magnitude of r1 prime dt. So times the square root of 2 dt. Then to get the second one, we're going to have our same bounds because t still ranged from 0 to 1. We're going to replace x with what we had in our parametric equation, so t. And then we're going to replace ds with the magnitude of r prime dt. So that's the square root of 1 plus 4 times 1 minus t squared dt. So at this point, we're just doing some integration to get the final answer. With this, I know I can add 1 to the power of t and then divide by the new power. So we get t squared times the square root of 2 divided by 2. And we're going to evaluate that from t equals 0 to t equals 1. Now, with this integral, we have to get a little creative there. Oh, whoops. Okay, that's why it was looking weird. Okay. Yeah, that's what x was in the second parameterization. All right, so with this one, we can actually do we could actually do a u substitution. Yeah, that's what we'll have to do. All right, so we can do a u substitution with this one. We're going to let u be equal to 1 minus t, which means du is going to be equal to negative dt. Since I don't have a negative, I'm going to move that over. Okay, so negative du dt. And then we can do our, yeah, and then we can do our replacements. So first off, negative. Okay. Remember, you have to adjust your bounds when you do a u sub. So if I plug 0 in for t, then I'll get u equals 1 minus 0, so this bound will be 1. If I plug in 1 for t, 1 minus 1, I get 0 for that bound. And so now so now it's not really that big a deal that that's negative because I can just switch these guys and change that to positive. All right, and then anywhere that I see 1 minus t, remember I can replace that with a u. All right. And now that we've done that, now that we've done that, we can actually do, yeah, basically another u sub on this integral. Because notice you have a quadratic in u inside the radical, and you have u outside the radical. So going back to this guy, if I plug 1 in and subtract plugging 0 in, I get just the square root of 2 over 2. So that's what we get for the first path. Now for the path backwards, I mentioned we'll do another one. Let's say we make this w. So w will be the inside of my radical. dw will be 8u du. I don't have the 8, I just have the u du, so I need to divide both sides by 8. So I get 1/8 dw is equal to u du. So remember, we can switch the bounds, change the sign. And at this point, this is going to be 1/8, which I'll pull out front, square root of w dw. Oh, other thing, I have to actually adjust these as well. Yeah. So 0, if I plug that in, I get 1. 1, if I plug that in, I get 5. Yeah. So always remember to adjust your bounds by plugging into that, whatever your u or w is, to get your new bounds. This just makes it so that you don't have to go back to the original variable at the end. So I have the square root of 2 over 2 plus 1/8. Remember, this is w to the 1/2, so I can add 1 to the power. That's going to be w to the 3 halves, and divide by the new power. That's going to be the same as multiplying by 2/3. We're going to use that and evaluate w from 1 to 5. So I still have my square root of 2 over 2 from the first path. I can bring the 2/3 out. So that's going to end up reducing to 1 over 12. And then I have 5 to the 3 halves minus 1. And that's our answer. So we were able to evaluate a line integral that went over two different pathways by just doing the paths separately and then adding them. All right. Now let's do one path integral where we are actually given our parameterization. All right, so let's say that we want to evaluate the interval over the path C of x plus 2 ds. And we're going to say that C, our pathway, it's another example, is given to us by a vector valued function r. So r of t is equal to ti plus 4/3 t to the 3 halves j plus 1/2 t squared k. And let's say that we're told in the problem that t is going to range between 0 and 2. So this is our given information. So from here, how do I do my path integral? Well, same idea, right? I need to come up with parametric equations, which in this case, because I was given my path as a vector valued function, I can just rip these components right off, and those are my parametrics. So I know that x is going to be equal to t. I know that y is going to be equal to 4/3 t to the 3 halves. And I know that z will be 1/2 t squared. Now that I know my parametric equations, I need to figure out the magnitude of r prime so that I can convert the differential as well. So that's going to be the square root of, and then remember, differentiate first. So derivative of x with respect to t is 1. Derivative of y with respect to t is going to be 2t to the 1/2. And derivative with respect to z is going to be just t. So if I expand this out, we get 1 plus 4t plus t squared. All right, that is the magnitude of r. So next, we have our bounds, we have our parametric equations, and we have our magnitude of r prime. So I can write my path integral now as just a regular definite integral. So we know t is going to go from 0 to 2. I know that I replace x with its parametric equation, so t plus 2. And I know I can replace ds with the magnitude of r prime dt. And looking at this, I know I'm going to do a u sub. Think about it, if you take the derivative of the inside of the square root, you get 2t plus 4, and that's a multiple of t plus 2. So that tells me that a u substitution would be helpful here. So off to the side where I did all my other side scratch work, we're going to do our u sub. So u is equal to the inside of the root, which means that du is going to be equal to 2t plus 4, which I'm going to write more conveniently. Dt, which I'm going to write more conveniently as 2 times t plus 2 dt. All right, so all I did is I factored a 2 out. Then I noticed that I only have t plus 2 dt in my integrand. So I'm going to divide both sides by 2 I get 1/2 du is equal to t plus 2 dt. So now I can make my substitutions. Remember, you have to adjust your bounds. So I'm going to plug 0 into my u equation. I get 1. Then I plug 2 into my u equation. 1 plus 8 gives me 9, plus 4 gives me 13. Then I make my substitutions within the integral. So the 1/2 I can pull out front, and this will be the square root of u du. All right, remembering that that's u to the 1/2, I know that I can add 1 to the power, so u to the 3/2, divide by the new power, that's equivalent to multiplying by 2/3. And then we're going to evaluate from u equals 1 to u equals 13. If I pull out the 2/3, this 1/2 times 2/3 will simplify to 1/3. Then if I plug 13 in, I get 13 to the 3/2. And if I plug 1 in, I get 1. So that is the value of that line integral. Pretty sweet. All right. So now we have, so now I'll go through and do an example that actually is an application problem. So in this next example, we're actually going to find the mass of a spring. Okay. So the spring is going to be our C, the path that we are integrating over, right? And in this problem, we're given that the spring is represented in, or as a vector valued function as 1 over square root 2 multiplied by cosine of ti plus sine of tj plus tk. All right, so hopefully at this point, we did so many of these in chapter 12 that maybe you recognize that that's a helix, right? So it makes like a spiral shape, kind of like an actual spring, right? So R of t is giving me the actual shape of the object whose mass I'm about to find. So that's our pathway. Remember, when we get mass, what are we integrating? We have to integrate the density, right? So we're told in this problem that our density as a function of x, y, and z is equal to 1 plus z. All right. So at this point, I can get my parametric equations pretty easily because we're given a vector valued function for our path. So we know that x is going to be 1 over the square root of 2 times cosine of t. We know that y is going to be 1 over the square root of 2 times sine of t. And then we know that z is going to be 1 over the square root of 2 times t. If I go to find my magnitude for r prime, all right, remember we want to take the derivatives of these. So the derivative of cosine of t would be negative sine of t. So I have the square root of 1 over square root 2 negative sine of t. We're going to square that. For sine of t, we know the derivative would be cosine of t. So this would be 1 over root 2 cosine of t. We're going to square that as well. And then for the last one, 1 over the square root of 2 times 1. Okay, and we're going to square that. So when I do that, here's what's going to happen. I'm going to get 1/2 sine squared t plus 1/2 cosine squared t. By now, we should know that we're going to factor that 1/2 out and make it our Pythagorean identity. So this whole thing is going to end up just being 1/2. And then when I square 1 over square root 2, I get 1/2. So this is the square root of 1/2 plus 1/2. in other words, 1, which is super convenient because then it tells me that ds is literally just dt. Pretty fun. All right, so then I can rewrite my path integral. Oh, wonky notation. Anyway, using oh, I forgot one other piece of given information. Yeah, this is also given. All right, so the range for t is 0 to 6 pi, which means that the bounds for our integral will be 0 to 6 pi. All right, and then we're integrating rho, so that'll be 1 plus z, okay? But we're going to replace the z with our parametric equation, so t over square root 2, or 1 over square root 2 times t. And then multiply by 1, which won't change anything, dt. So the antiderivative that we get will be t plus t squared over 2 square root 2. And we'll evaluate that from t equals 0 to t equals 6 pi. So plugging my numbers in, I get 6 pi plus 36 pi over 2 square root 2 minus, and then plug 0 in, you get 0. So altogether, my answer is going to be 6 pi plus 18 pi over square root 2. Right there, all I did is I divided 36 by 2. Right? And that's our answer. I believe your textbook also factors the 6 pi out, so there's that too. Right. And there we go. That is the mass of the spring. If you were to get a decimal value for that, that would be 144.47 in whatever units the base agree with what the units of our density were. All right. So now we're going to look specifically at line integrals as they apply to vector fields. So in the last video, we talked all about what vector fields are. They're basically represented by vector valued functions where all of the components could depend on x, y, and z. So rather than having to put everything back in terms of t, we dealt with it that way. I will say that a lot of times when we do line integrals with vector fields, it's still preferable for us to convert to our parametric in terms of t. Sometimes you don't have to, sometimes you do. We'll see a couple examples. So yeah, but the biggest thing that I want us to kind of understand here is that there's going to be a difference in notation when we're dealing with vector fields. So for the next example, let's do a problem that involves work. So let's say that we have a force field. Dun, dun, do, 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 do. All right, so this is a force field. Basically, the vectors that are assigned to each point in this field tell us the force acting on whatever object is at that point. All right, so here we're given that the force is given by the vector field negative x over 2I minus y over 2j plus 1/4 k. So variable force in our x and y direction, constant force in our z direction. And we'll say that the particle is moving along a pathway given by r of t, cosine of ti, plus sine of tj, plus tk. So basically you have an object that's moving along a spiral or a helix with some force acting on it. Right? It could be moving up the helix or down the helix. Actually, it'll be moving up the helix pretty much constantly. All right, but let's say that we are looking at that, right? We're moving, so that's the force field. This is the object's path. And we're taking this path specifically from the point 1, 0, 0 to the point -1, 0, 3 pi. All right, so it's like from the bottom of the spring, we're moving up, we're moving along the spring up until we get to this point. So that's our initial point, that's our terminal point. And this is our path. So we want to know the amount of work done by the force field. All right, so one thing that I want to remind y'all of is that work is the integral of force. So back in Cal 2, you learned how if you have a variable force in one variable, you could calculate the amount of work done over an interval, right? And usually that interval would be with respect to time or even x distance in one direction, right? Now that we're dealing with vector valued functions, our path integral is going to look more like this. And so our work is going to be defined as the integral over the path c, which we've defined here, of the force field dot dr. This is a different notation than what you're used to. And you see the dot there, there actually is a dot. It actually is a dot product, okay? But before I get into actually doing this one, I want to define what I mean by dr. So dr is going to be defined as the magnitude of r prime. Oops, not the magnitude. So dr is going to be defined as just r prime of t dt, right? Keep in mind we have to have two vectors so that we can do this dot product. So now that we've got, so now that we know what that is, let's do a setup. So I know that r prime of t, I can calculate component-wise. So derivative of cosine t, we get minus sine t, that's our I component. Derivative of sine t, we get cosine t, that's the j component, and then the derivative of t is 1, so that's our k component. So this is going to be our vector r prime. Our vector for the force field we're already given. So the work then is going to be the integral over this path c of the vector from our force field. So that was negative x over 2, negative y over 2, 1/4 dot r prime of t. So that's our vector negative sine of t, cosine of t, 1 dt. And instead of having the c here, we also could just write in our values for t, right? And taking a little adventure there. If we were to write out parametric equations for x, y, and z, we would find that x is cosine of t. We would find that y is sine of t. We would find that z is t. So if I look at the z coordinate at the starting point and the ending point, I've literally got my range for t. So 0, because that's the z coordinate in the first point, to 3 pi, because that's the z coordinate in the ending point. And to test it out, you could try plugging 3 pi into the x and y component. and you'd see that it would end up matching. Cosine of 0 is 1, sine of 0 is 0, cosine of 3 pi is -1, sine of 3 pi is 0. So the bounds for our integral are going to be from 0 to 3 pi. All right, other thing. I want everything in this integrand to be in terms of t because I'm doing an integral with respect to t. So rather than keeping these as x over 2, y over 2, before I take my dot product, I'm going to write them in terms of t. So negative cosine t over 2, negative sine t over 2, 1/4. Dot, negative sine t, cosine t, 1 dt. All right, and then when I do my dot product, remember, if you have your component form, you can just do first times first plus second times second plus third times third. So this will be the integral from 0 to 3 of first times first. So that's going to be positive 1/2 sine of t cosine of t plus second times second. So minus 1/2 sine of t cosine of t. And that's pretty convenient. Plus 1/4 times 1, which gives me 1/4. So that'll be 0, and we're left with just the integral of 1/4. And we're left with just the integral of 1/4, which would be t over 4, evaluated from t equals 0 to t equals 3. So my answer is 3/4. Oh, forgot my pi. No wonder I'm so hungry. I forgot my pi. There we go. 3 pi over 4. Yep, so 3 pi over 4, and then of course the units would depend on what the units of force were. Right, and as I am not your physics professor, I'm not going to talk about units. All right, so now that we've seen that, let's talk about something called differential form. So you've already seen kind of an odd, strange notation when we start taking our path integrals involving vector fields. Differential form is another way for us to write out a line integral. It's kind of shorthand, to be honest, but yeah. So I'm going to just do an example to show you. So this is what the notation will look like. You have your integral over the path c. Yep, so that's differential form. Kind of weird. It looks like it's wrong, but it also is kind of a convention um, in fields of study where you're integrating with respect to all sorts of different things. So with this one, we're told that our path C is defined by a vector value function r of t is equal to 3 cosine ti plus 3 sine tj, and t will range from 0 to 2 pi. All right, so if you remember your vector value functions from chapter 12, you might notice that this actually makes a circle with a radius of 3. And if you don't believe me, write out your parametric equations. X is equal to 3 cosine t, y is equal to 3 sine t. If you really wanted to, you could write this as x squared plus y squared equals 9. It's the same thing. So here we're actually going completely around the circle once, which means if we wanted to, we could put the little circle that way. Right, and then we could figure out if we're going clockwise or counterclockwise by just moving along the unit circle. Right, our cosines are going to be, or basically we're going counterclockwise. Yeah. All right, so you could write it like that as well, because this will be a simple closed path. All right, but anyway, we can actually use these these parametrics that we wrote out to write expressions for the differentials dy and dx. If I take the derivative, and it's kind of like how we do this with u sub, right? If I take the derivative of x, I'm going to get -3 sine of t dt. If I take the derivative of y, again, similar to how we do this with u sub, I'm going to get 3 cosine of t dt. So at this point, I know what I can replace dx and dy with. So going back, yeah. So going back to this, we can use our parametric equations to replace the x's and the y's. So I'm going to get put a big bracket around everything. Yep. So I'm going to get the integral, in this case, from 0 to 2 pi of y cubed. So that's going to be 3 sine of t cubed dx. So multiply by -3 sine of t and dt. All right, plus, then we're going to take our x, 3 cosine t, we're going to cube that, plus 3 times 3 cosine t times 3 sine of t squared. And then dy we can replace multiply by 3 cosine t dt. So at this point, I'm close off my big bracket. So at this point, I'm just going to do a whole bunch of simplifying, and then we're going to use some trig identities, and it'll look easier than it seems like it'll be right now. So 0 to 2 pi. So when I look at this first term, 3 cubed will give me 27. Multiply that by another 3, that'll give me 81. So -81 sine to the 4th of t. And then the dt's I'm going to kind of just write at the end. Think of it as like factoring out the differential. All right, and then for the second term, I'm going to have 3 cubed, that is 27, times another 3 will give me 81, cosine to the 4th t. So I get cosine cubed times another cosine, plus, and then here we're going to have 3 times 3 is 9, times another 3 gives me 27, times 3 two more times gives me 243, also known as 3 to the 5th. And then if I group together my trig functions, I have a cosine squared t, and I have a sine squared t. So all of that dt. So the first thing I noticed is that every coefficient in here is a multiple of 81. So I'll factor in 81 out. So I have 81 times the integral from 0 to 2 pi. That's going to leave behind cosine to the 4th of t minus sine to the 4th of t plus 3 times sine squared t cosine squared t, which I will write out as that quantity squared. The reason I want to do that is because now you might be thinking, oh, can I use a trig identity there? Yes, you can. But before we do that, reminder of a little factoring trick. I know that cosine to the fourth of t and sine to the fourth of t are something squared, right? So I could write this out as cosine squared t minus sine squared t times cosine squared t plus sine squared t, right? That's our difference of squares. Because remember, cosine of the fourth would just be cosine squared squared, and the same with sine of the fourth. Be sine of sine squared squared. So we can factor that using difference of squares, which is also convenient because we know that this is equal to 1. In a similar way, we know that this is very close to our sine double angle identity. The only thing that's missing is a 2 in front, which I can happily put there as long as I multiply it by 1/2 so that I'm not technically multiplying by anything other than 1. So we end up with 3 times 1/2 of sine 2t squared. Okay, now there's another trig identity that can simplify this even more. Cosine squared t minus sine squared t. We've done enough power reducing in our examples that hopefully many of you are able to recognize that this can be rewritten as cosine of 2t. It's the cosine double angle formula. And then with this one, if I square that 1/2 and bring it out, this 3 will become a 3/4. And at this point, I know that I'm going to have to reduce this using a power reducing equation, which is all based off of that identity, by the way. So we have 81 integral 0 to 2 pi cosine 2t plus 3/4 times, right? And remember, I can replace sine squared of angle with 1/2 times 1 minus cosine of double the angle. So 4t now. And at this point, it's perfectly fine for me to split this into two separate things. All right, and the 3/8 comes from multiplying 1/2 times 3/4. And now we're just taking the integral of trig functions. So antiderivative for cosine is positive sine. Since we have a coefficient, we divide by that coefficient. So get 81/2 sine of 2t. We're going to evaluate that from t equals 0 to t equals 2 pi. Then for this one, híjole. Okay. Just multiply it out. 243 over 8. And this antiderivative will be t minus 1/4 sine of 4t. And we're going to evaluate that from t equals 0 to t equals 2 pi. Now, very nice thing computationally is that sine of 4t and sine of 0 are both 0. So that whole first thing is going to be 0. As for this one, we already know that this sine term will result in 0 as well, because sine of 8 pi and sine of 0 are both 0. But we do need to put in 2 pi minus 0 for the t. And if I were to simplify this simplifies to 2 over 8 simplifies to 1 over 4. So we would end up getting 243 pi divided by 4 as our answer. And now I'll do one last quick example that also involves differential form. So for this one, we are going to evaluate over the path c y dx plus x squared dy. And here, the only information that we're given is that about c is that it follows a parabolic arc. Y equals 4x minus x squared from the coordinate 4, 0 to the coordinate 1, 3. All right. So this one, we don't actually need to mess with t at all. Like I mentioned, when we're dealing with differential form, sometimes it's easier to rewrite things in terms of t, sometimes it's not. But that last example, we also could have made it so that we use the equation of the circle and not have to replace anything with t. With this one, we can kind of do the same thing. I can actually rewrite the entire integral in terms of just x, because I, first off, already have something to replace the y with. And if I take the derivative of this, similar to how we do with u sub, I'll get something to replace the dy with. So derivative of 4x, we get 4. Derivative of x squared, we get 2x. And so I can replace the differential dy with this. And because I know the coordinates that we're starting at and ending at, I can actually take the bounds for my integral straight from that. If I'm rewriting the entire thing only in terms of x, then I only need to use the x coordinates for my bounds. Do remember, though, that you have to start from the initial and end at the terminal, even if it makes your integral look weird. So we'll have the integral from 4 to 1, not 1 to 4. If you write 1 to 4, then you need to change to a negative. Okay, and then y, we can replace with 4x minus x squared. There's already a dx there. Plus x squared, and I can replace dy with 4 minus 2x dx. So putting everything together, I have the integral from 4 to 1 of 4x minus x squared plus 4x squared minus 2x cubed dx. Square bracket, there we go. So I can combine like terms. If I want, I can switch my bounds and switch the sign of every term. Right? So if I do that, then I get positive 2x cubed. This was 3x squared. If I change the sign, it'll be minus 3x squared. And then this was 4x. Now we can write minus 4x. And from there, it's a simple integral. So add 1 to the power, divide by the new power, we get 1/2 x to the 4 minus x to the third minus 2x squared, and we're going to evaluate from x equals 1 to x equals 4. So if I plug 4 in, I end up getting 128, right? Because that's 4 to the 4 is the same thing as 2 to the 8. Divided by 2 to the 1 is 2 to the 7. 2 to the 7 is 128. 4 to the third is 64. And 4 squared is 16, doubled is 32. So that's what I get from plugging 4 in. When I plug 1 in, I get 1/2 minus 1 minus 2. So this will end up giving me 128 minus 96, which will be 32. And then this ends up giving me -5/2. So the minus will turn into a plus, and we have 5/2. So if I were to write 32 as something over 2, that would be 64 over 2. Add 5/2, you get, nice, 69 over 2. And that's the answer. So you see, we didn't have to mess with t at all in that one. If the information that we're given makes it easy enough for us to have y in terms of x, we can evaluate these line integrals in differential form without ever having to parameterize. So we covered a lot in this video. We talked about line integrals, which allow us to integrate over a path as opposed to integrating over an interval like in Cal 1, Cal 2, or over 2 and 3-dimensional regions like we have in this course. Whenever you evaluate a line integral, you need to know some information about the path that you're integrating over, right? It could be given to you as a vector valued function. It could be described to you in a way that enables you to write parametric equations. Once you know that, you have things that you can replace x's, y's, and z's with. You can also convert into ds, or your ds, which is typically the differential used for line integrals, by finding the magnitude of your position vector's derivative, right? So magnitude of your velocity, magnitude of r prime, and plopping a dt after it. Once you make all your replacements, you use the bounds on t to get the bounds for your integral, and then you just do an integration problem. And that's pretty much it. So go forth and practice these. Happy mathing.